So good afternoon, everybody. This is the beginning of everything. As you can see from the subtitle, I'm trying to give a brief description of the origin and the very early history of the universe. So let's start with a sky survey. This might look like simply a simulation of galaxies in the universe, but actually this is the result of mapping the positions of galaxies on the sky and determining their distances and using that to create effectively a 3D atlas. So although this is not real observations, this is an accurate indication of where the galaxies are, the close by few million galaxies, to give us an idea of how they're scattered throughout space. And I'm showing this to point out the fact that although there are lots of galaxies out there, possibly a few trillion or more, they're not evenly spaced, in that when we look around we see some areas that appear to be quite densely packed with galaxies and other areas that are relatively sparsely packed with galaxies. We see occasionally filaments and we occasionally see voids. Is it possible to understand where all of this stuff came from and why it's ended up looking like this? So if we look at, for instance, the Hubble deep field, we get a snapshot of galaxies. And remember, because light takes a finite length of time to reach us, if we're looking at objects that are a great distance away, then we're looking back in time as well. And the question we can ask ourselves is, the universe appears to be chock full of stuff. Stuff meaning generally loads of galaxies, each of which is probably made up of billions, if not trillions, of stars and maybe a whole load of planets as well. But can we understand how it all came to be? So I'm talking about the creation of the universe. When did that happen? 13.8 billion years ago. How long did it take to make a universe? Well, about 2 or 3 minutes, and you'll see why shortly. Where did it happen? Some people ask, well, where did the Big Bang take place? You have to remember the Big Bang was the origin of everything, and therefore the Big Bang happened everywhere. You can't point to one part of space and say it happened over there. Why did it evolve the way it did? Well, because of the laws of physics, and I'm a physicist, so I believe that the laws of physics essentially explain everything. So how do we know how old the universe is, and how do we know it took 3 minutes to make one, and how do we know how it's evolved? Again, we know all that because we've applied our understanding of the laws of physics to the universe as a whole. Let's just think for a while about nature. Nature being the study of the natural world, or if you like, the study of everything. Nature is not repetitive. If it was, it would be boring. So during the pandemic, you might think that one day seems pretty much the same as the next, but days, minutes, hours, seconds do not repeat. They might be similar, but you don't get the same thing happening all the time. But nature is neither unpredictable, it's not repetitive, but it's not unpredictable, in the sense that we can watch things happening in the world and we can say, based on our understanding of how the Earth is turning, we can predict that the sun will rise tomorrow. We might not see it because of cloud, but it will happen. If it wasn't, if it was unpredictable, then it would be impossible to make any sense of the world whatsoever. So if it was repetitive, it would be really boring. If it was unpredictable, we wouldn't be able to make sense of the world. So nature is somewhere in between. Nature is interesting. And we can ask ourselves, how does nature work? How does the universe work? What we're trying to get at are, what are the rules of the game that tell us this is how the universe works? So for instance, if we were thinking about this particular game here, if we didn't know what chess was, if we were an alien civilization and we took this picture of a chess game, would it be possible to work out what the rules of the game are just by looking at that picture? Probably not. At best, we can work out that the game seems to be played on a board of some kind, and there are various pieces that occupy certain squares, and there appear to be two different colours of pieces, but there's no way to work out what each piece does based on a static picture. And similarly, if we look at a galaxy, we can't say what's going on from that single picture of a galaxy. We might deduce that the glowing stuff there is from stars, but we can't work out a great deal about the dynamics of a galaxy and work out the rules of the game that tell us how that galaxy came to be simply by looking at a picture. If we come back to the chess game, instead of a picture, what if we had a movie? What if we could watch two people playing a game of chess? Well, then we would have a chance of working out what the rules are, even if we didn't know them in advance. Simply by watching what each player does, we can figure out what each piece is allowed to do, and ultimately perhaps we could work out what the goal of the game was, and hence the rules. But we can't really do that with a galaxy. We can't sit and watch it and say, let's figure out how that galaxy evolves by just sitting and watching it and seeing what happens. A galaxy might take a few 100 million years simply to rotate once, and it might take billions of years to evolve into the form it currently has. So we can learn a certain amount about the constituents of a galaxy by looking at individual stars, but we can't work out the dynamics, we can't work out the evolution, because we do not have the time to wait whilst we watch one galaxy. So again, coming back to the chess game, we haven't got time to watch a video of a game, so what's the alternative? Well, an alternative is instead of taking a snapshot of a game like this, and instead of taking a video of a game, why don't we take a snapshot of 1 billion games that are all taking place simultaneously, each at a different stage, one at the early stage of the game, one at the late stage of the game. This presumably is a late stage because the king appears to be toppled. If we had 1 billion photographs of 1 billion chess games, then we might stand a chance of working out the rules of the game for chess. And similarly for galaxies. Taking a picture of one galaxy isn't enough, but if we take a picture of hundreds or thousands or millions or possibly even billions of galaxies, there will be telescopes coming online shortly that will be able to build a catalogue of many billions of galaxies, then by looking at enough of them, even if we don't see them moving, even if we don't see them changing, if we have enough snapshots like this, and remember that we also have the ability to look back in time by looking at galaxies that are further away from us, then with enough information like that, we can stand a chance of working out how the universe works. But isn't it just too complex for us to get our heads round? Even if we just take a little snapshot of our immediate neighbourhood, not distant galaxies, but just a little bit of the gas and the stars in our neighbourhood, you might recognise this particular part of the constellation of Orion. Orion's belt is over on the left, the Great Nebula over on the right. How can we possibly make sense of that? How can we possibly work out what are the rules of the game that could possibly result in a system as complex as that? If we make an analogy and say, well, here's a mathematical collection of coloured pixels on the screen, some of you might recognise it as the Mandelbrot set, there's a particular mathematical equation that tells us how we can generate this particular pattern. If we zoom in, we'll realise that the pattern, although there are some regions of the pattern that seem to be very similar to each other, we can see a motif over here which seems to be reproduced down there. No part of this pattern ever reproduces. And we can zoom in, and we zoom in and see more detail. We zoom in and see even more detail. At no point do we see the same things coming back. We see similar structures in much the same way that if we look in a galaxy, we might see some stars that are similar to other stars, but they are not actually the same. So how complex a mathematical formula would we need to generate the entirety of the Mandelbrot set? Not simply the few million pixels that we're looking at here in the main image, and as we're zooming in by a factor of 1,000, by a factor of 1,000,000, by a factor of 1 billion or so. what complexity must we have in the mathematics that defines every pixel in the entire Mandelbrot set? Well, the mathematics required to generate the entire set is that equation there. Z equals z squared plus c is the only bit of maths you need to generate every pixel in the infinitely complex Mandelbrot set. So the point I'm making is, even though we look into the universe and it appears to be very complicated and very complex, that does not mean that the underlying rules of the game that we are trying to understand are necessarily beyond our comprehension. One of my favourite quotes from Einstein was that the most incomprehensible thing about the world, or the universe if you prefer, is the fact that it is comprehensible. Just because it's complex doesn't mean we can't understand it. Those are two different things. And essentially that's what physicists spend their time doing, looking at complex systems, asking what are the hopefully simple rules that tell us how this particular complex system works. So there's a flow of thought that we can follow when we're thinking about the universe. As of 100 or so years ago, we've realized that when we look at galaxies, they're moving away from each other. And so we conclude from that that the universe appears to be expanding. We can also do experiments here on Earth. We can bang rocks together, or we can fire fundamental particles at each other and see what happens. We can get an idea of what the world is made of, what the Earth is made of, and presumably what the Moon is made of, and what the Sun is made of, and what the Milky Way is made of. We can do experiments here on Earth that tell us about the fundamental building blocks of matter. We do have to make some assumptions. We can't start absolutely from scratch. We have to assume that if we start to understand the laws of physics, then the laws of physics in one place are the same as the laws of physics in another place. In other words, if the laws of physics for me were different than the laws of physics for you, then we can't make any progress. We can't make any advancements in our understanding of how the world works or how the universe works. We also have to assume that the laws of physics now are the same as the laws of physics in the past and in the future. If the laws of physics today were not the same as the laws of physics yesterday, again, we can't make any progress. If we let go of an apple and it gets pulled towards the Earth on Tuesdays, but it gets repelled from the Earth on Thursdays, if that was true and the laws of physics kept changing, we would not be able to make any sense of the world. So we have to assume that the laws of physics are immutable. They're the same for everybody, and they have always been the same and will always be the same. That's an assumption that we have to put in place to make any headway. Putting all of that together, our understanding of what's going on Earth, our observations of the universe, and our knowledge of the laws of physics, we conclude that the universe was created in a very hot, dense state 13.8 billion years ago. And ever since then, it's been expanding and cooling off. But the big question is, right, the universe is full of stuff. We look out there, and within the observable universe, we're not sure if the universe is infinite or not, but we can see a certain part of the universe. So let's just talk about the observable universe. Everything that's within something like 100 billion light years diameter, a large sphere of that sort of diameter, everything that we see in that sphere, all of the superclusters of galaxies, all the stars, all the dust, all the gas, all the planets, everything, where did all of that stuff come from? That's the question we're trying to answer. And in doing so, we can ask the question, well, how far back in time can we go? If we think we understand the laws of physics now, based on the experiments we do, etc., how far can we go back before we say we're not really sure whether the laws of physics still apply? How far until we give up on the physics we think we understand? Can we go back to the first billion years? In other words, if the universe is 13.8 billion years old, can we go back 12 and a half, 13 billion years? Yep, no problem at all. Can we go back to the first 1 million years of the existence of the universe? Yep, no problem. What about the first 1,000 years? Yep, no problem. What about the first year? Yep. What about the first day? What about the first hour? What about the first minute? What about the first second? Yep, to the best of our understanding, the laws of physics that we understand today still held at that point. What about the first millisecond? Yep. What about the first microsecond? Yep. What about the first nanosecond? We're now talking about the first billionth of a second after the Big Bang. Are we fairly confident that we know what was going on at that point? Yep. What about the first picosecond? Okay, at this point, we have to put hand on heart and say we don't really know what was going on when we get to this sort of point in the universe. Before the first picosecond, before the first 1/1,000,000th of a second, we're not actually sure what was going on. After that point, from that point onwards, we're on fairly solid ground. And the main reason for that is because we can test our hypothesis. If we think we know what was going on, we can test things in the laboratory to confirm if our understanding is right or not. Before the first picosecond, we really don't understand what was happening. Beyond a picosecond, we think we're okay. So that was a very long introduction to give you an idea of what I'm thinking about and how I'm trying to structure this talk in terms of, can we understand how the universe came to be and how it evolved for the next few billion years. I'm just going to spend one slide coming up next to introduce a few basic ideas which are necessary for what we talk about later. Then I'll say what happened in the first fraction of a second, what happened in the first few seconds, what happened in the first few minutes of creation. We'll then change gear because we'd be here all day if we carried on at that rate. We'll then fast forward to a point 377,000 years after the Big Bang. There's a very precise reason why we've chosen that number. And again, we'll change gear again and then very briefly talk about the next 13.8 billion years. So here's the few basic ideas, some of which you probably know, maybe not all. So we'll start with a few things you probably know. We are made of atoms. We are made of molecules. Molecules are made of atoms. Okay, and an atom is made up of a positively charged nucleus and negatively charged electrons buzzing around it like bees in a beehive. So we have known for quite some time that an atom is made of smaller things. An atom, despite its name, is not indivisible. It's made up of smaller objects. And in principle, we can take an atom and rip it apart and find out that it's made of a nucleus and electrons. As far as we understand it, electrons are fundamental particles. They're not made of anything. You can't take an electron, cut it in half, and look at what's inside. As far as we know, it has no insides. It is just a fundamental particle. However, the nucleus of an atom is a compound particle. In other words, it is made of something else. We can take a nucleus and we can probe what's going on inside a nucleus. These were experiments that were carried out in the early part of last century. And we now know that a nucleus is made of two types of particles, which we call protons and neutrons. We don't have to understand all of the nuclear physics and exactly what's going on. We're just looking at this Russian doll idea of at what point can we look inside things and find that they're made of something else. So a nucleus is made of two types of particles which we call protons and neutrons. And these are not fundamental either, in the sense that we could take either of those. Let's take the proton, for instance. We have found that the proton is actually made up of smaller particles which have this ridiculous name of quarks. And 3 quarks make up a proton. We don't have to worry about what a quark actually is, but just like an electron, a quark appears to be a particle which you can't cut in half and look inside. It appears that quarks do not have any compound structure. They simply are. They simply exist as fundamental particles. They do not have any substructure. So there's the Russian doll idea, that we can break things apart at various levels. And the important point as far as making a universe is concerned is that it takes a certain amount of energy to rip an atom apart. It takes more energy to take a nucleus and rip that apart into its constituent protons and neutrons. And it takes even more energy to take a proton and rip that apart and see inside its fundamental particles, its quarks that make up a proton. So there's an implicit energy scale here if we're thinking about this Russian doll. But remember, the universe starts out in a very hot state and is expanding according to our observations of what galaxies are doing. And because the universe is expanding, as you would expect for any gas, for instance, as it expands, it cools. So although it's low energy at the top and high energy at the bottom, that's not the order in which things are made, because the universe starts off hot and ends up cold. And to a physicist, low energy is cold and high energy is hot. Hot is just a way of saying all the particles that we're talking about have got a lot of energy. Or if it's cold, all the particles we're talking about have a relatively small amount of energy. So if the universe starts out hot and gets cold, what that means is the universe is built from the bottom up. To start with, the universe is far too hot, for instance, to make atoms. Atoms could not exist in the early universe because there was so much energy. The universe was so hot, all the particles had so much energy, an atom could not exist as an entity. It had so much energy it would instantly rip itself apart. And a nucleus would not exist in the early universe because it would have so much energy it would dissociate, it would rip itself apart into its constituent parts. Only when the universe has got cold enough will it be possible for quarks to make a proton. Only a little bit later, when the universe has got colder still, will it be possible for protons and neutrons to make a nucleus. Only later, when the universe is colder still, will it be possible for a nucleus and electrons to make atoms, and then atoms make molecules. So there's this idea that as the universe cools, it will be possible to construct these various structures from Russian doll small to large as we go up this vertical scale. And we can't sidestep this, we can't start making atoms before the universe has reached a particular temperature, because if it's hotter than that, the atom will simply tear itself apart. So that's the basic idea that we're going to use to see how the universe was built. We start at t equals 0, the moment of creation. But if we ask the question, what actually happened at t equals 0, it's perhaps no surprise to you to realise that science cannot provide a definitive answer. Whether we ever will be able to do so, you can either talk about metaphysics, or you can say your faith in physics is that someday we'll have an answer, or you might believe that we'll never actually know what happened at t equals 0. But we have studied small objects in the laboratory through a theory called quantum mechanics that tells us how things behave on a very small scale. And quantum mechanics tells us that it is possible for so-called quantum fluctuations to effectively borrow energy from nothing and use that energy to make particles. Energy and matter are essentially interchangeable in the early universe, because if you've got some energy, you can make some matter, and if you've got some matter, you can convert it back to energy. So it doesn't really matter as to whether we're talking about energy or matter. But this odd thing about quantum mechanics is that it tells us we can borrow energy from nothing. Perhaps you believed what you were taught at school when you were told that energy can be transformed from one thing, one type of energy, to another type of energy, but you can never create it and you can never destroy it. Well, you can say that's sort of true, but you can borrow it from nothing. You don't have to take that energy from somewhere else. Yes, that sounds really weird, and it sounds like a cheat. But quantum mechanics is really weird as far as we can tell. For the last 100 years we've been trying to prove quantum mechanics wrong, and so far it's met all of our criterion for being a perfectly sound physical theory. So maybe it was a fluctuation, and borrowing energy from nothing was how the universe came into being. How much energy can you borrow? Perhaps borrowing a small amount and making an electron is one thing, but how can you possibly borrow enough energy to make an entire universe? Well, it turns out that energy times time has an upper limit. In other words, you can borrow a lot of energy for a short time, or vice versa. It's a bit like borrowing money from the bank. If you were to borrow £1 from the bank, the interest wouldn't be very high, and you wouldn't be too fussed about paying it back very slowly over a long period of time. But if you borrowed £1 million from the bank, then of course the interest would be quite substantial, and there would be an impetus for you to pay that back as quickly as possible. Sort of the same thing with borrowing energy from the universe. You can borrow energy from the universe, but you've got to pay it back before the universe has noticed that it's gone. So energy times time has an upper limit. So the question is, well, how much energy did we borrow, and hence how long have we got to pay it back? Well, when you look at all the mass that's out there, the total energy in the universe is made of all the mass, which is positive energy, and all the gravitational pull of all the galaxies, which is negative energy. When you add it all up, what do you find? Well, the answer appears to be somewhere around 0. We're not absolutely sure, but it appears to be about 0. So maybe the total energy budget of the universe is 0, in which case we've got plenty of time to pay it back. Maybe that's an unsatisfactory answer. Well, yes, it's got to be an unsatisfactory answer because we don't know. This is purely speculation. Let's move forward from time equals 0 to time equals that many seconds. In other words, 10 to the minus 35 seconds after the Big Bang. The universe has gone from something with essentially no size and is now expanded until it's about the size of a golf ball. By the universe, that's my shorthand for everything that we now see in the observable universe, everything that is now within 40 or 50 billion light years of where we're sitting at the moment, everything that we currently understand in our observable universe used to be in a volume a few centimeters in size. In other words, everything used to be a lot closer. Trying to imagine everything in the observable universe inside a golf ball is a bit tricky. But that appears to be the best theory we've got as to how the universe expanded from the early days to this unimaginably small length of time later. This analogy of thinking the universe as being very compact, I tend to think of it as a golf ball, which is very convenient because the universe had dimples in it, just like a golf ball has dimples. Okay, it's not quite the same thing because in a golf ball, the dimples are simply in the surface of the golf ball. In the universe, the dimples are analogous to the small variations that we have in the universe. The universe wasn't perfectly uniform in this very early time period. There were small differences in the density and the temperature across the universe. So let's just call those dimples rather than refer to them as microscopic, tiny variations in density and temperature. Eventually, when the universe is a lot bigger, these small variations, these small dimples, will give rise to the variations in density that produce the galaxies, that produce the clusters and individual galaxies, and ultimately the stars in the universe. But that's a long way in the future, of course. Let's jump now to the first picosecond. So we're now talking about 10 to the minus 12 seconds after the Big Bang. The universe is now substantially bigger than a golf ball. It's now the size of the solar system or thereabouts. Yes, of course, the solar system doesn't yet exist because we still have simply a very hot ball of very energetic particles. We don't have any structures within there yet. And you may also notice that this is a tiny length of time for the object to expand from the size of a golf ball to the size of a solar system. So you might already deduce that the universe is expanding much, 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 much faster than the speed of light. It's allowed to do that. The universe can expand at any speed it wants to. The temperature continues to fall. As the universe expands, the temperature falls. And we're talking about what's in this ball, what's in the golf ball, what's in this ball that's the size of the solar system. It's effectively a soup of fundamental particles. Energy was borrowed, energy makes matter. What sort of matter? Well, it could be electrons, it could be quarks, in principle it could be other particles. We're not going to worry too much about that for the moment. We're just saying it's a soup of fundamental particles, and there are various types of them swimming around. The temperature tells us how much energy we have, how much energy each of those particles have. And the reason we think we understand from 1 picosecond onwards what's going on is because this is the point at which the amount of energy that each of those particles has in this quark soup, that's roughly the energy that we can give a particle in a particle accelerator, such as the Large Hadron Collider, for instance. In other words, if we want to test out any ideas we've got about how do particles behave when they have this much energy, from now on we can give those particles that much energy in a particle accelerator. Up to this point, the particles were so energetic we can't reproduce those conditions on Earth. But from this point onwards, we can. So everything up to this point is pure speculation. From this point onwards, we can start to test things by doing experiments on Earth. And because we can test our ideas, that's why we believe we've got a pretty good handle on how things have gone from this point onwards. Okay, we've borrowed energy. Energy makes matter. Energy makes matter, matter makes energy. E equals mc squared. Back and forth and back and forth and back and forth. Any amount of energy we have can in principle make matter and antimatter. Antimatter is simply the opposite of matter. For instance, your body is made up of protons and neutrons and electrons. Well, there are also opposites of those in the sense of, although there is a fundamental particle which we call an electron, and we're made up of a lot of those, there is another fundamental particle called an anti-electron. Sometimes it's called a positron. It looks exactly like an electron, except it has the opposite electrical charge. Instead of being negatively charged like an electron, it's positively charged. And every fundamental particle has this mirror image particle as well. So matter and antimatter are made by energy, and matter and antimatter can annihilate with each other and make energy. So there's this conversion back and forth and back and forth. I don't know how to represent energy in a PowerPoint presentation, so I'm just going to use a capital E. So energy can make matter and antimatter. Probably not a tangerine and an anti-tangerine, but the point is it doesn't actually matter what the particle is. It might make an electron and an anti-electron, or it might make a quark and an anti-quark. And those particles, one of matter and one of antimatter, can annihilate with each other and produce energy. And that energy is probably in the form of electromagnetic radiation in terms of light. And that light, that energy, can make another particle of matter and antimatter. Not necessarily the same pair again, it might make something else. Probably not a hot dog and an anti-hot dog, but again, just a particle and the anti-version of that particle. Back and forth and back and forth, matter and energy, matter and energy. Originally, the matter and the antimatter are made in exactly equal amounts. But somehow, via a mechanism that we don't quite understand, matter gained an excess over antimatter. In other words, when we think of all the particles that were made, all of the particles of matter, and we think of all the particles of antimatter that were made, at some point in this early universe they got slightly out of balance. Here I've showed it as a 10% difference between matter and antimatter. It's not as big as 10%, it's not 1 part in 10, it's more like 1 part in a billion. Might not sound like much, But it's rather important because if you think of all the matter and antimatter particles, they are all going to annihilate with each other and produce energy, produce light, if you like. But that matter particle left over, that tangerine on the end, hasn't got an antimatter equivalent to annihilate with. So we end up with a universe full of energy, full of light, and a little tiny amount of matter. But that tiny amount of matter is everything we see in the observable universe. All the galaxies, all the stars, all the planets, you and me, are that little bit of matter on the right-hand end there. So there's an awful lot of light out there, there's an awful lot of photons of light flying around the universe, and there's probably 1 billion or so photons for every particle of matter. But that particle of matter is just what's left over when all of the rest of the matter and antimatter have annihilated. So it's just as well a little imbalance did occur because we are the result of that tiny imbalance that occurred at this very early stage of the universe. Let's move forward to a millisecond. What happened after a millisecond? Well, matter and antimatter are continuing to pop into and out of existence. Matter to energy, back and forth and back and forth. Eventually, protons and neutrons, which are made up of quarks, they can start being made because the universe is now cold enough that we can make a proton and we can make a neutron. We don't have to worry about the specifics of the details, but if we had a bag of 3 quarks, and it doesn't matter particularly why they're coloured red, green and blue, and it doesn't really matter what the symbols U and D actually mean, but a particular configuration of 3 types of quark in a bag is what we label a proton. We call that particle a proton. And a slightly different configuration of quarks, if we have one that's labelled U and a couple that are labelled D, then that particular bag of 3 quarks we call a neutron. So at this point in time, 1 millisecond after the Big Bang, it is possible for some of these quarks to hang on to each other and actually start making protons and neutrons. But it's still hot enough that they are quite happily, readily transforming back and forth and back and forth. There's enough energy to allow these little bags of quarks to, if you like, mix together and change such that protons can change into neutrons and neutrons can change into protons. We're now moving forward to 1 second after the Big Bang. The universe has been cooling all of this time, remember, and now the universe is only 1 billion Kelvin. And if you think that sounds ridiculously hot, bear in mind that the centres of some massive stars might have a temperature, a core temperature, as high as that. Our sun, core temperature, only of order tens of millions of Kelvin, but larger stars will have hotter cores. So although that sounds like a ridiculous temperature, we're now getting to something that we can actually get a handle on. And although it's 1 billion Kelvin and it sounds ridiculously hot, it's a lot colder than the universe was. And it's now too cold for protons and neutrons to readily swap back and forth. In other words, we're starting to freeze in the sort of structures that we've made up to this point. Protons happen to be a little bit lighter than neutrons. How do we know that? Because we can measure them in the laboratory. We can take protons and neutrons and we can measure their masses, and it turns out that protons are a little lighter than neutrons. And to the best of our knowledge, there is no reason to assume that protons 1 billion years ago are any different to protons today, or any different to what protons will be in 10 billion years' time. So because protons are a little bit lighter than neutrons, although the universe is making lots of protons and lots of neutrons, because they're slightly different mass, the universe makes a slightly different number. And it turns out that if one particle is a little bit lighter than the other, the universe says, that's great, I'll make more of those. Why should the universe make more protons? Here I'm labelling the protons in red and the neutrons in blue, and it turns out the number that are made at this particular point in time are, roughly speaking, 3/4 protons and 1/4 neutrons. And I'm just showing you a representative set of 16 particles here. Why should nature choose to favour the lighter particles when it's making all of these? Well, if you think about it, it's the same reason as, for instance, if a ball is on a slope, the ball will choose to roll downhill. Why does a ball roll downhill? It's because the valley is a lower energy state than the top of a mountain. So the ball will want to go into the valley. It won't roll up to the top of a mountain. It'll roll into the valley because a valley is a lower energy state for the ball to be in. And nature always favours the lowest energy. And in this context, energy and matter are almost interchangeable. And if nature always favours the lower energy, it's also fair to say nature favours the lower mass. So if it's making lots of particles, it'll make more of the lower mass. It's only smaller by 0.1%, but at this particular temperature, we can calculate that that would predict that we should be getting 3/4 proton, 1/4 neutron. For every kilogram of stuff that's made, 3/4 of it should be protons, 1/4 of it should be neutrons. We can move forward a little bit to of order 100 seconds, so now we're talking about a couple of minutes or so after the Big Bang. Neutrons are not stable. Some neutrons will change spontaneously into protons. How do we know that? Because we watch them do that in the laboratory. We can do lots of experiments, and we know that the slightly heavier neutron can change into a slightly lighter proton. That will happen if you stick a neutron on its own in the middle of nowhere. So the ratio of protons to neutrons changes slightly. Of the original 16, we had 12 red and 4 blue, but 2 of the blues have now changed to reds because 2 of the neutrons have changed into protons in this sample set of 16. So we now have a new ratio of protons to neutrons after 2 or 3 minutes of the universe's existence. What happens next? Well, as the universe is cooling down, it is now just about cold enough for protons and neutrons to want to stick together. Up to this point, the universe has been too hot, and any attempt at protons and neutrons sticking together, they would have been so energetic they would have flown apart again. But after 2 or 3 minutes, the universe is just about cold enough that protons and neutrons can start to pair up. And again, by doing lab experiments, we know that 2 protons would love to be married up to 2 neutrons. Now that the universe is only about 100 million Kelvin or so, it's come down from, the last note was 1 billion Kelvin, it's now 10 times colder, nuclei can now start to form. And we know that 2 protons and 2 neutrons is a very stable structure. Again, we can measure that in the laboratory. You either call that particle an alpha particle, or you talk about 2 protons and 2 neutrons as being the nucleus of what we call helium. So we're not thinking about the electrons just yet, but if we label them according to what element they will be called when we think of them as the nucleus of an atom, then what we get is 2 protons pairing up with 2 neutrons. But that, of course, leaves us with 12 bachelors. Those protons on the left haven't got any neutrons to pair up with. The universe did not make equal numbers of protons and neutrons. So now some of the neutrons have been lapped up to make the nuclei of helium atoms, and we're left with a load of bachelors who haven't got any neutrons to pair up with. So if this is correct, if our understanding of physics is correct, if this is how the universe was made, then we can predict that the universe should be full of that much helium and that much hydrogen. After 3 minutes, the universe is not hot enough to change that ratio. After 3 minutes, the relative abundance of hydrogen and helium in the universe has been set. It is now frozen, as it were, at that particular value. If you wait long enough, some stars will start changing hydrogen into helium, but that's a long time in the future. As of this point, and as of the next few billion years, the amount of stuff in the universe ought to be 3/4 hydrogen and 1/4 helium. If you work it out in terms of the numbers of particles, or if you think about it in terms of kilograms, it really doesn't matter. If you look at all of the stuff in the universe, most of the stuff in the universe is gas. Stars and dust and planets occupy a tiny fraction of that, so most of the universe is gas. And when you see how much of that gas is hydrogen and how much of that gas is helium, what do we find when we observe? We observe 3/4 of it is hydrogen and 1/4 of it is helium. In other words, this so-called Big Bang theory predicts that that's the way the universe should be, and that is what we observe. That is one of the key reasons why we believe that the Big Bang theory is the theory that tells us how the universe came into being, because it makes a prediction that we can test. We can actually observe the universe, and it does come out to be that particular ratio. So that gives us confidence that we are dealing with the right elements of physics. We're now going to jump a long way forward to 377,000 years after the Big Bang. Basically because nothing interesting happens for the next 1/3 of a million years. We've made all the hydrogen, we've made all the helium, they are now fixed in terms of their abundance, and nothing much changes other than the universe continues to expand and the universe continues to cool down. Eventually, the universe gets to the point where it's cooled to about 3000 Kelvin. That particular time is 377,000 years after the Big Bang. Why is 3000 Kelvin important for the next step of how the universe changes? At that particular temperature, it is now possible for a nucleus, whether it be hydrogen, a single proton, or whether it be the nucleus of helium, 2 protons and 2 neutrons. It is now possible for a nucleus to hang on to some electrons. Those electrons have always been there in the soup, in the background, but now it's possible for a nucleus to hang on to them. Up to this point, the universe has been too hot, and any nucleus that tries to attract an electron, they'll simply be ripped apart. But now the universe is cold enough, only 3000 Kelvin, now it's cold enough for a nucleus to hang on to an electron. So for the first time in the history of creation, atoms can now exist at this 377,000 year point. That's important because up to this point, the positive charges and negative charges were all floating around in a plasma, but now we have the positive and negative charges in an atom, which is electrically neutral because the positives and the negatives effectively cancel each other out. An atom is electrically neutral. At that point, we no longer have the universe as a plasma, we have the universe as a gas of individual atoms, positive and negative charge. At that point, the universe becomes transparent for the first time in history. Up to this point, light has been rattling around inside this plasma and it found it impossible to escape. But light, as soon as the universe becomes transparent, light can escape and no longer is contained within this plasma, but effectively no longer gets scattered by all the positive and negative charges. The light, if you like, is released, if you want to think of it that way. So there should be an aftermath, a glow, if you like, of the Big Bang that is visible, because all of this light was released at approximately the same time, and then it's been flying around the universe ever since. So what sign have we got that we can actually see this light that was released? What are we expecting this light to look like? Well, how hot was the universe when the light was released? It was 3000 Kelvin. What happens if you take something and heat it up to 3000 Kelvin? It ends up white hot. If you heat something up to hundreds of Kelvin, it starts to get a dull red. If you heat it up, it starts to go orange. If you heat it up thousands of Kelvin, an object will glow white hot. So the universe was white hot when the light was released. So in other words, we would expect to see visible light. But the universe has expanded quite a lot in the time it's taken from when the universe was 377,000 years old to today, the universe is now 1,000 times bigger than it was back in that time. If the universe is 1,000 times bigger, then the wavelength of light is now 1,000 times longer because the light is stretched by the expanding universe. So what was visible light with a wavelength of order microns is now light or electromagnetic radiation with a wavelength that's not microns but is now millimeters. It's microwaves, and that is the cosmic microwave background. It is the echo or afterglow, if you like, of the Big Bang, because at one particular specific point in time, the light was released, and that is what we see in the microwave background. We see it as microwaves rather than visible light, simply because it's been stretched by the expanding universe. And it's not uniform everywhere. When we look at the microwave background and we measure, some areas are a little bit more intense, other areas are a little bit less intense as to how many microwaves we see. We can interpret that as being these are different temperatures. Remember, the golf ball had dimples in it? There were variations in density and temperature in the golf ball. Now the golf ball has expanded to something substantially larger, but we're still seeing the imprint of those dimples from the golf ball imprinted into the microwave background. So we observe the microwave not just as an interesting peculiarity of the universe, because it tells us, it gives us a piece of evidence that indeed the universe was born in a Big Bang, because that Big Bang predicts that we should see microwaves, and that is indeed what we do see. Not perfectly smooth, but those variations are the variations that we saw earlier in that all-sky map. Those variations are simply the dimples in the golf ball that are now imprinted on the microwaves. And that's why it is important to study the microwave background, because that gives us an ability to probe what was going on in that early universe. If we think about the consequences, the golf ball started with dimples and that ended up with variations in the cosmic microwave background. What happened as the universe continued to expand beyond that? Well, if we run forward with a simulation over billions of years, we see those small variations in temperature and density ultimately give rise to what we now call the cosmic web. In other words, if we start with a simulation here of a small part of the universe in which there are small variations in density that are seeded into the simulation, if we let gravity do its stuff, what do we find? We find gravity starts to collapse areas and it concentrates the matter into particular regions, which ultimately will become the clusters and superclusters and individual galaxies that we see today. And we notice that the galaxies aren't uniformly spread throughout the universe. We tend to get clusters, we tend to get filaments, we tend to get voids. Just like we saw in the 3D atlas that I started with, of that's what the universe is actually like. We can understand that based on, if we start with a golf ball with a few variations and let gravity do its stuff, we find we end up with a structure that is not unlike the structure we see in the universe. If we think about what's going on in our locality, this is a little map with the Milky Way in the center there. We have a few small galaxies around us. We have the Andromeda Galaxy in our local group off to the right there. If we change the scale somewhat and look a little bit further afield, we realize that we are a very small part of a much bigger cluster. Off to one side there we see the Virgo cluster, and down in the bottom left we see other clusters, the Fornax cluster, Eridanus cluster. And of course we see large regions which don't seem to have many galaxies at all. We can start to see this structure of a filament, indicating that we've got these very high density regions where lots of galaxies were made, and we have other areas where there is less galaxies. Again, if we scale up and look in a bigger scale, the Virgo supercluster is now in the middle of that diagram, and we see lots of other areas, lots of other clusters, and we see huge regions which appear to be almost devoid of any galaxies forming. And all of that, the dense regions of superclusters, the voids where there's very little going on, all of that is the result of the tiny fluctuations in density that we saw in the original golf ball, and we also see imprinted on the cosmic microwave background. On a huge scale, the universe looks relatively uniform and quite foamy. But if we start zooming in to see what's going on smaller scales, this is a numerical simulation which appears to be a good approximation to how the universe actually looks. On a large scale, it's relatively uniform and foamy, but the more we zoom in, the more we see individual structure of galaxies and clusters of galaxies where these filaments meet, where matter has produced a concentration of matter to form the initial stars and galaxies. We can get a feel for that for this particular simulation by zooming in from scales of order billions of light years. We can zoom into this foamy structure, this so-called cosmic web. This particular simulation is called the Millennium Simulation, simply because this calculation was done about 20 years ago at the turn of the millennium. There were plenty of other simulations that are also trying to reproduce, can we understand the structure of this cosmic web, these filaments, these voids, these knots where the filaments meet, which appears to be where the clusters and superclusters start to form, and can we understand the details of galaxy formation and star formation in these regions. We're zooming in now to the point where instead of looking at billions of light years, we're now zooming in to the scale of order millions of light years. So we're now starting to look at the scale of individual galaxies rather than the scale of clusters. And again, if we zoom out from that particular meeting of filaments, we can see how that fits into the grand scheme of the universe on a large scale, which looks on a large scale pretty much the same everywhere. The top right. So good afternoon, everybody. Look in this direction, we see the same as if we look in that direction. On small scales, things look different galaxies in different areas, but on large scale, the universe looks the same everywhere. What happens for the next 13.8 billion years from the early formation of the universe to where we are now? Well, essentially, if the Big Bang Theory tells us we are going to make shed loads of hydrogen and quite a bit of helium as well, if we start with hydrogen, then we know that if you take a cloud of hydrogen and collapse it, you'll make a star. So basically, as long as we start with enough hydrogen, then we can understand galaxies, we can understand stars, we can understand planets, we can understand trees and mountains and snowflakes and rainbows and cats and okay, probably not cats. I don't think we'll ever understand cats. But as long as we start with enough hydrogen, we can pretty much trace how everything else came to be. Yes, there are still some details we need to think about. There's some aspects of cosmic evolution where we've got the big picture, but we perhaps haven't got some of the details. But essentially, if you understand the origin of hydrogen, then you can make a story for the origin of everything else in the universe. So let's just remind ourselves how that timeline looked. We've gone over a ridiculous timeline from 10 to the minus 35 seconds at one end to billions of years after the Big Bang on the right-hand side, and that's where we are now with the green line. So back on the left-hand side, we have the cosmic golf ball. Everything that we now see in the observable universe was much closer together, only a few centimeters or so distant from each other. It was a soup of quarks. Well, it's called quarks. Actually, it's a soup of quarks and electrons. And the universe was too hot for those quarks to do anything until we get to the point of order a second or so, where quarks can start forming protons and neutrons. And if we wait a few hundred seconds, those protons and neutrons can start making atomic nuclei. And at that point, we can predict that most of the nuclei should end up as hydrogen, and a little bit, 25%, will end up as helium. And nothing much happens for a third of a million years until the nuclei start to catch some of those electrons and the universe is cold enough for atoms to form. Once atoms form, the universe is transparent. As soon as the universe is transparent, the light is released, and we see that today as the cosmic microwave background. There's then a little period of the so-called dark ages, because it takes a little while for all of that hydrogen to eventually collapse into stars, and once we have stars, the universe lights up once again. So there's a period of dark ages where the universe is quite dark until the first stars are born. And again, there's active research in trying to understand how the first stars came to be and how the first galaxies were formed. But that's the whole picture in one ridiculously compressed timeline. Yes, we still have questions. The jigsaw is not really complete. We've got the corners, we've got the edges, we've got most of the landscape, but there's still a few pieces of sky that are missing, and this is rather annoying because we can't quite finish the jigsaw. There are some remaining questions, and they are quite serious questions. Why did matter win over antimatter? Why did they get out of balance? Why didn't the universe make the same amount of both? In which case, all the matter and antimatter would have annihilated, and we would be in a universe which was full of light and nothing else. Well, I say we. Of course, if there was no matter, there wouldn't be any we. The universe would simply exist as a very large sphere full of light, and there would be nothing else. So it's just as well that matter did win over antimatter, but why did that asymmetry arise? I haven't said anything about dark matter. I've been talking about everything that we can see in the universe, all the stars, all the galaxies, all the dust, all the gas. We can't see dark matter, but we believe it's out there because it seems to be causing the galaxies to rotate at the wrong speed, or at least not the speed that we would expect. And what is the deal with dark energy? Why is the expansion of the universe not slowing down, as we would assume under gravity? The expansion of the universe appears to be accelerating. This is something that was only found out 20 or so years ago, and we don't understand why that is. So the talk is titled The Beginning of Everything, but I tried to emphasize that I was talking about everything that we can see in the observable universe. But everything we can see in the observable universe is perhaps only 4% of everything that's out there. The other 96%, dark matter and dark energy. The other 96% is still a bit of a mystery. But that's another story. Thank you for listening.
That was great.